like to ask the presenters to just spend 5 minutes, and then after that, we're going to sound the horn, and the presenter just really has to stop. We'll move on to the next presenter, and we won't be able to ask any questions during the presentations themselves, but again, you're going to have a chance to do that afterwards. Okay, so let's go.
Okay, good afternoon. I'm Taejin Kim from Seoul National University. Today I'm going to present my ongoing work named Lifetime Improvement Techniques for Multiple SSDs. As price per byte of NAND flash memory is continuously decreasing, multiple SSD-based storage systems are emerging. To achieve higher reliability or performance, system-level redundancy techniques such as RAID are adopted for multiple SSDs. However, different from single SSD, the lifetime of SSDs become more problematic for multiple SSDs. For example, application writes are amplified by multiple disk management layer, which may significantly degrade the lifetime of SSDs. Basically, the application writes are amplified by the FTL, but for multiple SSDs, an intermediate layer is needed to manage the multiple SSDs, and the writes are amplified by this layer. As a result, the lifetime of each SSD is reduced under the multiple SSD environment. In order to address this lifetime reduction for multiple SSDs, we propose an integrated lifetime improvement approach. In our approach, various techniques for lifetime improvement, such as compression and deduplication and DPS and dynamic throttling, will be integrated at the multiple disk management layer like RAID or at a single SSD layer. By this integration, we reduce more P cycle of NAND flash memory so that it effectively increase the lifetime of SSD-based RAID device. As a part of approach, two preliminary techniques will be presented in the following slides. One is optimizing the RAID to be aware SSDs, and the other one is integration of compression and deduplication in a single SSD. Firstly, how RAID 5 amplifies the application data will be presented. For the evaluation, Linux soft RAID utility called MD is used. Our preliminary results show that the application data is amplified by about 2.4 times on the RAID 5 MD. This amplification is mainly because of two reasons. One is the writes during the initialization. During RAID 5 initialization, MD reads the entire space of all disks except one and writes the entire space of a disk to synchronize the parity information. The other reason is frequent parity updates due to the large stripe unit. MD sets 512 kilobytes as a default stripe unit size. Based on our evaluation of relationship between the stripe unit size and number of parity writes, such a large stripe unit increases partial stripe writes, resulting more parity updates. Based on our preliminary evaluation, we propose SSD-aware RAID 5 MD optimizations. First, the initialization writes are not necessary for SSDs because the initial data is guaranteed by trim command. For example, the initial data is not guaranteed for hard disk drives, so initialization writes are required to correct the parity information. However, if we issue trim command during the initialization, the initial data is guaranteed by 0 and they are correct, so the initialization is not necessary for SSDs. Second, the number of parity updates can be reduced by using smaller stripe unit. MD sets large stripe unit size by default to exploit superior performance of hard disk drives for sequential access, but it increases the chance of partial stripe writes. In this example, 3 parity writes occur for 3 application writes. Because of SSDs do not benefit as much as hard disk drive from sequential I/O and have a limited number of P cycles, a small size chunk would be more advantageous for SSD lifetime. By using page-sized stripe unit, we need only 1 parity write for 3 application writes. As a result, the initialization writes are removed and parity writes are reduced about 50% in our evaluation. Another technique for integrated lifetime approach is dedupe-assisted compression called DAC. DAC integrates delta compression and deduplication to achieve higher compression ratio. In order to efficiently determine data similarity, that uses fine-grained fingerprinting. For example, if we compute a fingerprint for 1/4 data of each page, page B is selected as a reference page of page A since it contains 3 identical data chunks. By applying delta compression to page A and B, we only need to write less than 1/4 data of page. Using DEC, about 17% of data is reduced compared to the compression after deduplication. To conclude my talk, we proposed an integrated lifetime improvement approach for multiple SSDs with 2 preliminary techniques. For the future work, we will develop integrated multiple SSD or lifetime improvement techniques, including integration rate with deduplication, DPS, and dynamic throttling schemes. So, thank you.
Good afternoon, everyone. I'm Dong-Young from Songyungan University. This is the joint work with Jang Woo-min and Professor Young-Ik Today, I'll talk about a new buffer replacement algorithm for NAND flash storage devices. These days, NAND flash storage devices are widely used in modern computing systems because they have many technical merit. However, traditional buffer replacement algorithm in operating system are not suitable because they consider only the characteristics of hard disk drives. So we propose the TS clock buffer replacement algorithm, which consider the characteristics of NAND flash storage devices. So to improve performance and lifetime of NAND flash storage devices, we have 3 techniques. First, we exploit the traditional clock algorithm and maintain page in recency order for high cache ratio. Second, we prefer to evict clean pages than dirty pages. So we use a reference count for each page rather than reference bit of clock replacement algorithm. And reference count is differently set reference count is differently set for giving different chance. Finally, to exploit the NAND flash storage, to exploit the characteristic of NAND flash storage devices, we have 2 hands, such as T-hand and S-hand. T-hand is similar to the hand of traditional clock algorithm, and the S-hand employed to evict dirty page in a block sequentially. Let me give you an example of flash-friendly eviction. In this example, the buffer cache is full and cache miss occurs. To select the victim candidate, T-hand scan pages in recency order and check each reference count. So 53 pages is swapped, and each reference count is decreased by 1 because each reference count is not 0. And 67 page is selected as victim candidate because each reference count is 0. After selecting victim candidate, we check whether the victim candidate clean or dirty. So current victim candidate is dirty. So S-hand scan dirty page belonging a block and check the reference count. So 66 page is evicted instead of the victim candidate because each reference count is 0. And we ship the page because we ship the page to maintain recency order. Finally, a missed page is inserted the position of T hand, and then T hand is updated for selecting next victim candidate. For evaluation, we implemented TS clock and 4 replacement algorithms. And as graph shows, TS clock maintains higher cache-hit ratio than other replacement algorithm, as well as it improved performance of NAND flash storage devices. Especially, TS clock outperforms the state-of-the-art algorithm by up to 22.7%. To evaluate the lifetime, to evaluate how the TS clock affect the lifetime, we simulate the erase count. And this picture clearly shows TS clock extends lifetime by up to 40.8%. Today, I did not describe the details of other processes, such as calculating reference count and selecting a block for 30 pages. Please refer to fourth section for more details. Thank you.
Hi, my name is Douglas Ostad. I'm a PhD student from Florida International University. It's not coming up there.
There is a little switch.
No?
No.
No? It was up there, right? Yeah, it was up before, right?
Yeah, hold on. Where is it?
What was it? This happened before?
No.
You want to try again? Pull it out and put it back in?
No, wait.
There? Good? Okay, sorry about that. So I'm going to talk to you real briefly about my work involving host-side flash translation and I/O scheduling for SSDs. So some characteristics that are problematic for modern systems, SSDs cannot write in place. They have to erase a block before they can overwrite it. Also, reads are oftentimes an order of magnitude or more faster than writes. And a logical block address does not have any meaning as far as where the block might be physically in the device. So in order to solve this, modern SSDs provide what's called a flash translation layer, which allows the SSD to present a generic block device to the operating system. So here's what the architecture looks like. So we have the I/O stack on the host, and it's going to send requests to the device, which is going to be received by the flash translation layer. And that's going to do all address mapping as well as scheduling, garbage collection, and wear leveling. And so this is what the internals of the device might look like. You might have one or more flash packages, which contain one or more flash die. And the die is the parallel element of operation, so they can each operate completely independently. And then one flash die might contain several flash planes, which include flash blocks and flash pages. So what are the limitations of this system? Well, for starters, the OS has no idea what's going on inside the SSD. It doesn't know where logical blobs are mapped. It doesn't know if there's garbage collection that's ongoing. It doesn't know if there's some die that are being overworked and some that are being underutilized. Meanwhile, the device has very limited resources. It might have a small processor, very little memory, a very small cache. So this limits the intelligence that it can implement as far as scheduling algorithms. Also, there's no coordination, so there's no way for these two to share any sort of knowledge as far as workload or ongoing operation. So the solution that we've proposed is to optimize I/O performance through a sort of teamwork, holistic approach where we can combine the power of the OS and the host machine with the knowledge of the FTL. So this is what we want our architecture diagram to look like. As you can see, the scheduler has been moved to the I/O stack so that it can receive requests directly from the generic block layer. And inside, it contains the same map as the FTL, as well as some other structures that help it make smarter scheduling decisions. And then it's going to forward requests directly to the driver, which will send the request to the device. And the device is just very simple. It sends the request directly to the die with no computation, similar to how a disk would operate. So there's 3 optimizations that we aim for when we were designing the system. So one is load balancing. The other is promoting reads before writes, since they're much faster. It's sort of like a shortest job first. And finally, to prioritize system I/O so that garbage collection can be pushed to the background in a non-blocking manner. So this is how we achieve load balancing. So each die has its own queue. So as requests are received, they're decoded by the map to figure out where they are physically, and they're queued according to their die. And in this way, we can limit how many outstanding requests there are per die so that we don't fill up the cache with too many requests that are pointing to the same die. And in this way, we can achieve a sort of rudimentary load balancing between all die. In order to prioritize reads, we have a separate queue for writes. Since writes don't have a physical address yet, we can queue them separately, and we only issue them when a certain die is underutilized. And in this way, we can guarantee that writes are promoted first. And then finally, for system I/O, so we have a separate set of read queues and write queues for all requests that originate from garbage collection. And in the same way, they're given a lower priority than the system I/Os are given. And in that way, again, we can guarantee that they're serviced later in a non-blocking manner. And this makes things appear much faster to the applications that are using the SSD. So our current status, so we've developed a prototype kernel module for Linux, which does all of this. We're currently working to evaluate it. So we're collecting traces and validating a simulator using DiskSim. And we also have an ongoing project to develop an FPGA SSD where we can program different architectures to evaluate the comparison. And so finally, I'd like to thank my laboratory back home, Visa, and Marvel Semiconductors here for providing the schematics for the internals of the SSD. Thank you.
Good afternoon. Today I'll briefly introduce about accelerating graph computation with emerging non-volatile memory technologies. The graph is kind of data structure which represents the interaction and communication between objects. It is widely used in many areas, but there are some difficulties to do the graph computation in a small node system. Usually the graph size is as large as tens of gigabytes, and their access pattern is highly unpredictable. So during the computation, storage should be accessed frequently and randomly. But the current fastest SSD still requires tens of microseconds per access, so this is very long latency in computing intensive workload. And moreover, current SSD uses file system, which is not allowed the direct store of the pointer-based storage. So pre and post-processing before and after the data transfer is needed. And we found that this overhead consumes a significant part of the total execution time. Only about 10% of the execution time is wasted used for real graph computation, and the remaining part are wasted to solve this overhead. So in my study, I tried to reduce this overhead by modifying the storage structure, applying the new memory. Instead of using flash memory, which has very long access latency, I tried to use the racetrack, which is one of the candidates of near ideal memory. And by applying this memory, I try to quantitatively analyze the energy and performance of the graph computation. And in addition to this memory, I also use the pointer-based graph representation when I store the data in storage. This pointer-based graph representation take advantage of the byte addressability of the rest string memory, and so it increased the compatibility between host and device. So the overhead of the pre and post processing is significantly reduced. So I simulate the graph computation based on pin-based cycle accurate simulator. So this is the result. As you see, by removing the pre and post processing and reducing the I/O, the total execution time is significantly reduced. And moreover, energy is also saved because the execution time is reduced, and the workload of the CPU is also reduced. In addition to this, I also trying to do the in-storage processing. Some graph computation workloads such as PageRank is very simple, so we don't need to use the host CPU, which is very expensive. Instead of this, I added some simple FPGA, and using the device CPU, I try to do the graph computation within the storage device. This is the result. The total execution time is further reduced because even though the CPU execution time is increased, because the data transfer time is reduced, so the net gain is reduced. Energy consumption is also reduced as previous case. But this is some ideal case study. So now I'm trying to do the similar work on PRAM. PRAM has a very asymmetric performance, but the critical part is the read access latency, and I think that this is very good candidate for graph computation. So this is the end of my presentation. Thank you.
Sorry. Down. That's okay. Yeah, I think you can. Should I start? All right. Hi, my name is Babak. I'm a fourth-year PhD student at the University of Illinois, and we are currently working on this project called Automatic Generation of I/O Kernels from HPC Applications. I work with Marcus Neer, who is a professor at the University of Illinois and also Director of Math and Computer Science at Oregon National Lab. Just as the motivation of this work, we all know that parallel I/O has also become a performance determining factor of modern HPC, mostly because HPC scientific simulations are dealing with very, very large data sets, and they have to do checkpointing and also input and output of this data. So it would be very good if we can derive an I/O kernel automatically from these HPC applications. By I/O kernel, I also mean pseudo applications in another terminology. So the main reasons of this being a good thing to have is that we can have better I/O optimizations, performance analysis, I/O auto-tuning, application debugging, storage system evaluation, and also it will enable ease of collaboration between HPC community. But the question is it possible to derive these I/O kernels of HPC applications automatically or not? If yes, then we will always have the latest version of I/O workloads rather than having I/O kernels that are outdated. And also, this is going to be an I/O complement to the HPC application co-design effort, which is led by the DOE. So let me just go over the related works first, because extensive research has been done here. On the right side, you will see you see the I/O stack of a modern HPC application. And let's start from the bottom up. So at the very low level, we have the file system level trace and replay tools. We can point to TraceFS from Stony Brook University, for example. At the POSIX level, there are a lot of trace and replay tools. One important one is Parallel Trace from Carnegie Mellon. And we also have some trace and replays at the MPI/IO level, such as Scala H-Trace and Riot.io. Our work is mostly at the application level. We use HDF5 library, which is very well used and in the HPC community right now. We have also a work on doing generating skeleton I/O from Oak Ridge National Lab, which uses Adios library. So the overall architecture of our system is that you have the full application. We have developed a recorder library that is linked to your application, and once you run your application, it generates I/O traces on each of the ranks. And then we have a merging tool that tries to merge these traces into a single trace so that the code generation can be done on that single trace. And then once you do that, you will have the application I/O kernel. So let's go over each of these components. Our recorder is done. We have developed a multi-level tracing library which works at each of these levels of the I/O stack that you saw. For example, HDF5 level, whenever you call a function, it will record it and trace it for you. We also need MPI/IO and maybe POSIX/IO. The main reason that we need MPI/IO is that we need that to preserve the synchronization and dependencies at the application. But we envision the actual trace and replay at the HDF5 level, which is the highest level. Once we have all these traces generated using the recorder, we need to merge them in order to be able to generate the code. So we have developed this merging tool that does that for us. Currently, it works both for HDF5 level and MPI/IO level, but it has to take care of very different scenarios. For example, on the picture you can see on the left, if you have a function that is being called on all the traces, you can easily merge them and just put them in the single trace. But there are a lot of cases that that's not happening because different processors are doing either different operations or one operation with different arguments. So we have to take care of that. And then once you have this single trace, we are working on a code generation tool which generates a single program multiple data MPI code for it. It has to allocate the buffers based on the sizes that are recorded in the trace, and the data is definitely randomly generated because we are not storing any data on the trace files. Again, we think that HDF5 is easier to do this process for because HDF5 is higher level. We have each object has an integer identifier. Thanks. Sure.
It was your one here, but it's Hi, I'm Florin Isailă from Argonne National Laboratory and University Carlos III, and I'm going to present Clarisse, cross-layer abstractions and runtime for input-output software stack of extreme-scale systems. This is joint work with my colleagues from Argonne and also my colleagues from University Carlos III from Spain. Our work is motivated by some current problems in the storage input-output stack of high-end computing systems. My speaker from before has already introduced the stack. You can see in the figure that the applications, high-level I/O library, and input-output middlewares, such as MPI/IO, run on compute nodes. Then file system calls are typically forwarded through input-output forwarding infrastructure to input-output nodes, which mount the file systems which run on storage nodes. There are several problems of this input-output stack. One of them is that, as you could see in the picture, the input-output stack is distributed over different types of nodes. This means the path from the compute nodes to storage is long. It goes over several networks and over several memories. And also, all this path is implemented in several layers of the input-output stack. These layers are typically implemented independently. This means the developers are applying their optimization at these layers, but currently there is no possibilities of doing some cross-layer optimizations. We're trying to address these problems by the main goals of our project. One of them is to enable global optimizations of the software input-output stack. We are targeting an evolutionary approach in which we try to build on existing optimizations in the current input-output stack that could be enhanced by having global information. But also we target to design novel cross-layer control abstractions and mechanisms for supporting data flow optimizations. And I cite here collective I/O, data staging, and exploiting the data locality in the stack. Here is a high-level overview of our approach. What we'd like to do is to intercept the calls at different stack layers, and over there to add some local control modules which should be in charge of controlling data-related policies such as buffering, caching, prefetching. And these local control modules should communicate through a communication backplane between each other or through a centralized controller. For the communication controller, we think of using the communication backplane that is currently implementing in the Argo project in Argo National Laboratory, which is a project which tries to design the next operating system for the exascale machines as a combination of local operating systems and runtimes. And finally, a controller which is logically centralized but not necessarily centralized physically, which should actually centralize information about the system and then try to enforce decisions at local control level. Here I show a short overview of some related work. It is not everything. Our work is similar to software-defined networking, in particular OpenFlow, which also targets global control based on separation of control and data flows. Our work is maybe closely inspired with IOFlow, done at Microsoft Research, which is a software-defined storage architecture for virtualized data centers. Fast Forward project targets to redesign the storage input-output stack by using some of these software layers. Then I cited Argo and Hobbs is another project. Both of them try to design the next operating system for the exascale machine. And finally, there are some cross-layer optimizations for current input stacks, such as parallel auto-tuning or reduced performance interference. I finish here. I'm going to be at the poster session. Please feel free to come by, and I'm looking for your feedback. Thank you very much.
So, okay. Oh? Oh, okay. Good. Okay. So today we'll talk about Hyper-NVM and hypervisor managed non-volatile memory. I'm Haoyi Huang. I'm assistant professor at George Washington University, and this work is a joint work with two of my colleagues, Tim Wood and Guru Venkataramani. So what motivates our work? One of the reasons is the cloud computing going to be here and going to be here for many years to come. And we have seen many data centers are running a large number of VMs, and all these VMs are doing many of these VMs are doing data-intensive jobs, and in turn, this creates a big pressure on the memory systems, and we always want high-performance memory subsystems to retain all the hard data that we need. But if you look at the virtualization, there are many problems, although it has many benefits, but it also comes with some problems. One of that is not every hardware resource is created equal. That means some resource like CPU, we can easily share that. And we can share in very fine granularity, like tens of milliseconds. And for storage, and in the last several days, we have seen many interesting work in this domain. So there are a lot of interesting effort into how we're going to improve storage virtualization. But when you look at a memory system, memory is always shared in a very coarse granularity, in big chunks and over a large period of time. And because each machine hosts tens of VMs in general, so that means we always have a memory pressure in the system. And as we all know, and from the keynote today, and the last several papers, we see that Flash is going to be here, and there are new emerging memory systems going to come, like PCM and other type of memories. The question really is how can we utilize them in the future data centers? There are also other observations we made. One of that is the resource can be underutilized in virtualized data center. The figure on your left shows a free memory that we observe over a month in a GW data center. We have seen for some machines, here we show 5 machines. For some machines, the free memory is about 80%. Some of them has large fluctuations over that time window. There are also performance interference among virtual machines. The figure on your right basically is some numbers we presented in our supercomputing paper in 2001 that we see their performance slow down on Amazon EC2 instance when you have many co-located I/O-intensive virtual machines. And last but not least, everybody in this room know that when we're dealing with non-volatile memory, we have reliability issues. We have this asymmetric read and write performance, and also this performance process variance that we have to worry. So naturally, since we are talking about virtualized data centers, and because the hypervisor or VMM that sits between the virtual machines and the underlying memory architecture, a promising approach is to make hypervisor more memory aware. And in this framework that we propose is we let the OS and applications, we enable them with some specific APIs to utilize the memory system more intelligently. In the same time, we give more control to the hypervisor, and with the help from the hardware monitoring tools, as well as from upper level, the more smarter algorithms that we can monitor the memory access patterns either online or offline, doing online or offline analysis, and enable policy for optimized resource usage. And this is our ongoing work, and we have many different projects in this domain. And this one is Mortar that we will present in VE next month. And basically what we are doing here is to use the key value store interface and give more memory to let hypervisor to manage. And this work is mostly done by 2 PhD students, Jim Hang and Arsen Upel. Jinho Hang. Jinho is working for IBM now, and Arsen is here today and is looking for a summer internship. And we have some performance numbers in the poster, and you are welcome to stop by our poster, and we will be very happy to talk to you about this more. Thank you.
So this presentation is about Hybris, which is a robust and consistent hybrid cloud storage system. And this is a joint work from Eurocom Institute and the NEC Lab Europe. So despite the well-known benefit that comes from the adoption of cloud storage, there are several different concerns. These concerns are about mainly security. In fact, you should be worried about integrity, availability, and confidentiality that should give away to your data cloud storage provider. Another important limitation that limits the adoption of cloud storage by the application provider is the weak consistency guarantees. In fact, in this context, we often talk about eventual consistency. So several kind of solutions have been explored during the last years to face this kind of problems. Some have engineered a way to to set up a private cloud on trusted premises. Some others have been thinking about the hybrid cloud approach, which entails using both private cloud resources and a public cloud. While some other researchers have been thinking about an approach which consists of scattering all your data across different public clouds while distributing also the trust among them. And Hybris try to retain the benefits of all these different approaches. So how does the Hybris architecture look like? Basically, the Hybris client scatters the data across different untrusted public clouds, which can be Byzantine faulty and which can exhibit eventual consistency, while keeping metadata on trusted private premises, which are modeled as crash-only faulty and which can guarantee strong consistency. The metadata we are talking about in this context is pretty small, as it just consists of cloud pointers, the data version, and data hash. And as you can see from this picture, we used Apache Zookeeper to implement our reliable metadata service, and we also used memcached to boost data retrieval performance. So thanks to this kind of architecture, Hybris is strongly consistent because it leverages strong metadata consistency to mask the weak data consistency provided by the cloud platforms. Hybris exposes a multi-writer, multi-reader key-value API, and it tolerates up to F-malicious clouds by writing, in the common case, to up to F+1 clouds and reading from only one cloud. In the worst case, that is to say, in case of faults or inconsistency, it writes at most on 2 F+1 clouds, which is the optimal efficiency also in case of crash faulty models. So we implemented Hybris in Java, and we evaluated the scalability of the reliable metadata service. And as you can see from this graph that refers to a test about the write operations, it can scale up to 25 kilooperations per second. And also the read scalability is up to 180 kilooperations per second. So to perform this kind of test, we used low-end commodity servers on a OpenStack cluster. So that would be all. As you can see from this slide, there's a research report draft and the code of Hybris, which you can check out from GitHub. Thanks.
Already did, but Sorry. No? Oh. Yes. Okay, sorry about that. Okay, good afternoon, everyone. My name is Thiratat Patana Anek, and currently I'm a student at the University of Chicago, and I'm here to talk to you about a really cool work we're working on called I/O sheltering, which we try to solve the disk performance issue in multi-tenant storage system. This work has been done with Shalfanchan Nora Sandler and my advisor, Professor Haredi Gunavi. So first, let's talk about the problem. The problem that we have here is that random write does too many random seek. The prime example of this is Amazon EC2 ephemeral storage, which are left unused because of this issue. So why random write are bad? In our opinion, it is bad because of the strict coupling of durability and consistency. Durability means that for every durable request, the content has been written to the disk, while consistency means that after the crash, the content can be read from the exact same location on the disk, in this case, block number 10. This strict coupling in I/O semantic are hard to solve, and they can lead to disk contention. Whenever we have a random write, we have no choice but to interrupt these nice sequential I/Os and seek to the right location on the disk for random writes. And this can cause performance degradation that we talked about earlier. This is where I/O sheltering comes in. With I/O sheltering, we decouple durability and consistency by providing durability shelter. With I/O sheltering, sequential writes are left untouched, while random writes are written sequentially to a pre-allocated durability shelter, and you can think of this space as a mini logFS. After that, when the disk is less busy, we can write them to the final and correct location on the disk later. As you can see here, we preserve both property, durability, and consistency, and also improving the performance at the same time. So why are we doing this now? We can do this now because we now have enough memory space to pin all the shelter random write in the system. Moreover, majority of the applications are designed to do sequential I/Os, so I/O shelter is more lightweight. And thirdly, because we already have data replication in place, slower start is more tolerable. And finally, because of bi-addressable non-volatile memory, we now have a better place to put in our shelter indexes. So let's see how I/O sheltering did. With our micro benchmark consisting of one sequential tenant and multiple random tenants, we plot the throughput of sequential tenant between unmodified Linux and Linux with I/O sheltering. Our early prototype gives us over 9x speed up for sequential tenant without any loss of durability for random tenant as well. Furthermore, we also simulate I/O sheltering using 1 hour industrial block level traces, and we get significant throughput improvement for all 3 traces that we try on. For future work, right now we try to integrating I/O sheltering with journaling and file system. And we also try to explore many other policies that we can use I/O sheltering with. And yeah, thank you, and we'll see you at the poster session.
So my name is Michael Sevilla. I'm at UC Santa Cruz working under Scott Brandt, Carlos Malton, Ike Nassi, and Sam Feinberg, who's actually at HP Storage. So we're interested in automatic load balancing in a distributed system, which is oftentimes a multi-objective optimization problem. We feel that this is an issue in many distributed systems today. So for example, how does caching affect my performance, or how does the workload affect where and when I should move different resources? So we want to use Ceph as a prototyping platform for exploring and investigating resource migration and load balancing in a distributed system. So Ceph stripes and replicates data across a reliable object store called Rados. Cephfs is the POSIX-compliant file system that uses Rados. It decouples metadata and data I/O, so all metadata operations go to a separate metadata cluster, which you see in the bottom right. This metadata cluster exposes a hierarchical namespace to the user using a technique called dynamic subtree partitioning. In this scheme, MDSs, or metadata servers, manage subtrees in the namespace. So in this example, this yellow MDS is handling this yellow subtree. So why do we want to use Cephfs? Well, because it's one of the most advanced metadata infrastructures, and it was built with file system locality in mind. Also, many of the tools for migrating resources are already implemented. So for example, it can detect hotspots using counters, and it can already migrate directories around the metadata cluster. So let's zoom in on this metadata cluster a little bit more. This is the same picture as before, but now we're focusing on the cluster. The cluster is connected to clients to service metadata operations, and it's connected to the object store so that it can periodically flush its state. So let's say that we want to move this yellow subtree that's sitting on this yellow MDS. The load balancing question that we want to answer is, where and when should I move this subtree? Cephfs can already migrate this subtree around the metadata cluster, and the way that it does this now is it calculates load on each MDS, and if the load exceeds some threshold, then it migrates the subtree to the next MDS, kind of round-robin fashion. Load is calculated using CPU utilization and request rate and latency. But we argue that load balancing is contingent on many other trade-offs. So for example, each of these MDSs has their own set of resources like network, memory, and cores. And these should be accounted for if we're trying to figure out where and when to move these different subtrees. Furthermore, each of these MDSs may be doing different things. So for example, this gray MDS may be handling a bunch of client requests, so its cores may be overutilized. This green node may be flushing its state, so the network may be a little congested. This pink node may be handling a bunch of subtrees, so maybe it's experiencing memory pressure, and this magenta node may be handling other background jobs. And it may even be better just to keep this subtree on this yellow MDS, because Cephfs does aggressive metadata caching. So if we migrate the subtree to a different MDS, then we may have to fetch some metadata objects. So we've outlined some of the requirements for our implementation. Our implementation should be distributed so that we don't lose any of the benefits of having a distributed metadata cluster. It should be low cost so that we can calculate where and when to move these subtrees on the fly. And it should acknowledge multiple objectives. So we're thinking of using or constructing Pareto optimal surfaces where the axes are resource utilization or event frequency. And then that would require identifying the trade-offs that we're dealing with. And to identify these trade-offs, we'll probably use performance counters or some kind of a timing analysis. And then we'll want to resolve these trade-offs using different migration heuristics. So we'll look to machine learning for some help with that. So here's some preliminary results. We just started playing around with Cephfs just to see where we're at. In these experiments, we're doing 50,000 file creates in the same directory. The x-axis is the wall clock time on both graphs, and the y-axis is the load. Each color represents the load measured on a different MDS. So in the top graph, at 25 seconds, MDS 0 realizes that it's overloaded with a bunch of requests, and then it starts distributing the load to 4 other MDSs in the cluster. And the job finishes at about 280 seconds. In the bottom graph, all we did was we switched the logical ordering of the MDSs. So what used to be MDS 0 is now MDS 4, and that changed something drastically in how the load got distributed. So the load got distributed later, and it distributed more load to less MDSs. The job actually finished faster, so we think that's a result of caching. So this shows us that where and when we move resources really does matter, and that extensive load distribution does not always equal better performance. So again, our goal was we wanted to have autonomic load balancing in a distributed system, so we're using Ceph as a prototyping platform, and we propose that any solution should be distributed, low cost, and multi-objective. And come visit my poster and give me some feedback. Thanks.
Good afternoon. My name is Gregory Jean-Baptiste, and I'm a PhD student from Florida International University, and I'm going to present my work on data deduplication and solid-state drive storage caches. So just a little background. Cloud systems commonly use network storage, and this provides efficient storage utilization, fast VM migration, and improved data reliability. However, because of the high consolidation in the cloud, there is a lot of contention for storage resources, which typically leads to I/O performance degradation. To deal with this issue, well, here's a diagram of how the current setup typically is. And to deal with this issue, one common solution is flash caching, which is basically using a solid-state drive as a client-side cache. And as you all know, solid-state drives are faster than hard disk drives, and they are also more energy efficient. DM cache, which was an example of this solution developed by colleagues at Florida International University, provides transparent client-side flash caching and supports dynamic virtual machines with efficient cache storage sharing. And here's a diagram of that. So here's pretty much the same thing, except in the actual physical machine, we have a solid-state drive that a DM cache is using to provide the virtual storage. One of the challenges with this solution is that solid-state drives are much smaller compared to typical back-end storage devices, and they're also small compared to the amount of data that several virtual machines might be using in a single physical machine. Also, they have limited lifespans. As we've discussed many times today and yesterday, they're limited based on the program erase cycles, and the writes over time wear out flash memory. So our way of dealing with this issue is to perform deduplication in the cache device. So we do it inline during operation, and basically what we do is we detect redundant insertions and we cancel them, and instead update the cache with pointers instead. So that with less writes, we get less frequent erasures and a longer solid-state drive lifespan. And with less duplicate data in the cache, we have more space for unique data, and that can possibly lead to a higher cache hit ratio in the long run. So here's a diagram of the architecture that we're proposing. So basically what you have is a physical host with several virtual machines running on it, each one with a logical volume attached. And they're all attached to DM cache, which is on top of the solid-state drive. So what you have is several cache blocks inside of the SSD can be shared by multiple source addresses. That means several VMs can be using the same cache block if the data that they're using is the same. And in order to find out which cache blocks hold the same data, we use fingerprinting, which is basically applying a hash function to the data inside of the cache block and keeping track of which fingerprints map to which cache addresses. That way, when an insertion comes, we can get its fingerprint and quickly find out if there is a match already inside of the cache. And it also uses a copy on write mechanism so that if one of the VMs tries to overwrite the data in that cache block, then we can simply find out if that cache block has more than one VM using it. And if that's the case, then we simply eliminate that mapping and provide a new cache block, a fresh cache block for the VM that attempted to do the write. So far, we've done some preliminary tests that are comparing the original DM cache to the enhancements made with deduplication. And we've gotten a slightly better performance using IOZone and doing read tests over iSCSI. So the current status of the project is that we've already implemented a prototype, and so far the results are promising, including that includes the speed up that we perceived and the space that we're saving inside of the cache. And future work involves coming up with a better cache insertion and cache replacement algorithms. Right now, the cache is using LRU, which may or may not be the best solution anymore, since a cache block might be shared by several VMs, and evicting it right off might not be such a great idea. So we're going to have to look at different options and test those as well. That concludes my presentation.
Hello everyone. Today I'm going to talk about HFLIR, a high-fidelity block I/O replay tool. My name is Alireza Haqduz from University of Minnesota, and this is a joint work between our research center and NetApp. So workload replay. So in this project, our goal is to reproduce previously captured workload from a SAN controller, and then we are trying to reproduce this workload in one of the connected servers to this test SAN controller. So there are some use cases for replayer tool. For example, it's going to be useful for benchmarking and performance evaluation. It would be useful for performance validation with some realistic workloads, and it basically avoid expensive reconfiguration for very, very large test applications. So we have some fidelity goals in our mind. The first one is that we need to preserve original request ordering in the replay workload in order to maintain the sequentiality or the randomness of the request. The other goal is we need to reproduce the same load profile when we replay back the workload. And finally, our last goal is to maintain the inter-arrival time between consecutive I/O requests in the reproduced workload. So there are, of course, a couple of challenges. The first challenge is that SAN workload is a random mixture of I/O requests without a unique and reproducible order. The other challenge is that the inter-arrival time between consecutive requests are sometimes even shorter than a system call latency. Therefore, we cannot do it with a single thread. And the other challenge is that the I/O workload in our case has been captured from a SAN controller, and then we need to replay it back from one of the connected servers. As a result, the storage stack latencies and queuing effects are missing in the SAN trace, and yet has to be considered in the replay process. And the other challenges is we need to minimize the non-deterministic impact of the non-real-time OS on our replay tool. And finally, we need to determine block I/O request dependencies in order to replay according to the dependency of the request. We made some observations, and these are key observations. I have more detail in my poster session. The first observation is that a storage stack cannot increase load more than maximum supported SCSI tag size. As a result, queue sizes need to be tuned accordingly in the storage stack. The other observation is that system throughput reduced significantly at a high load. As a result, replay with the highest speed does not necessarily increase throughput in our case. And finally, we realize that the SCSI device driver does not necessarily issue commands based on the arrival order. Therefore, some requests can get out of order inside the device driver queue. And the final observation we made was that this system call latency is very unpredictable, and we need to work around that. I have I just have very high level of the approach. Detail is in my poster session. So we deployed multiple worker threads to submit these I/O requests, and we deployed a separate harvester thread to process the completion events and keep track of the number of in-flight I/O requests. To control the replay speed, there are three approaches. The first approach is load-aware approach. approach, which basically dynamically match number of in-flight I/O requests with the given load profile in the original trace file. The second approach is time-aware approach, which basically just take a look at the timestamp in the original trace file and then issue requests based on the timestamp. And the last approach is the hybrid approach, which basically combines the previous two methods. We realize the last method is giving us the best accuracy to reproduce the same workload. And then we introduce a new technique called request bundling. We basically bundle all consecutive I/O requests as long as the inter-arrival time between those requests are shorter than a predefined threshold. For example, in this trace file, these three requests in the top and those three requests at the bottom are very close with each other. And if we submit these requests in one thread, there is some race condition. In different threads, there is some race condition between thread 2, 3, 4, and here 3, 4, 1. Therefore, it's better to combine all of these requests in one big bundle and submit them within a thread. And finally, these request bundling eliminates some extra user kernel mode switch and reduce race condition between worker threads. Thank you very much. And I would like to say that our tool, our replayer tool, is available for Clarisse member companies. Thank you.
So, good afternoon, everybody. Since I'm going last, I guess I don't have a time limit. My name is Pramod Mandagare, and I'm from IBM Almaden. And today I'm going to be talking about some recent work we are doing on adaptive backup management. Some background on the topic. We analyzed performance of backup servers, several hundred backup servers across several data centers spread across multiple geos. And we found a couple of interesting patterns where there's a lot of room for optimization. The first one is temporal skew. So if you look at the graph on the top left, it shows load profile of a backup server over a 24-hour period. And this is just a random sample we picked from one of the data centers. And the graph shows the number of active backups and the aggregate bandwidth consumed on the backup server at any point in time. The interesting thing about this graph is you'll notice that most of the traffic is at hourly boundaries, and the heavy utilization period is concentrated around a 3-hour window between 6 and 9 p.m. So what this means is these backup servers have to be provisioned for peaks, which is quite suboptimal. On the other hand, if you look at the graph at the bottom, this is a similar load profile of a different backup server in the same environment. And you see that the load profile here actually shows a lot of utilization, and it's a hotspot. So what I'm trying to emphasize here is there's very little load balancing across backup servers, and there's a lot of room for optimization in this space. So if you look at why these skews happen, both the temporal and spatial skews, the main reason is backups are usually managed by static policies, but the work that they're trying to do is dynamic. So specifically, if you look at backup scheduling, there are two paradigms, which is, number one, server-initiated backups. This is where the client declares a backup window of approximately 2 or 3 hours, and the server is free to do the backup anytime during that window. In this case, what typically happens is the client backup windows are becoming shorter and shorter as a result of global nature of business and lack of distinct idle times. So clearly, this server-initiated backup does not really play well with the clients. On the other hand, if you look at client-initiated backups, which is the push model, this is where clients trigger backups whenever there are significant events or on predefined schedules. What happens is this actually leads to hotspots on the backup servers themselves. On the backup servers, there's a need for distinct maintenance windows these are windows where backup servers themselves are backed up, or other maintenance operations such as asynchronous deduplication and content indexing are done. So what happens is, if you go with either only a server-driven approach or a client-driven approach, there's a lot of suboptimality leading to temporal skews. On the other hand, if you look at the spatial skew, which is basically imbalance between backup servers, the main reason for this is backup configurations are set at provisioning time, and they're never revisited after that. But if you look at any client, and if you look at it across multiple points in time, you'll see that the nature of the client changes, or the amount of data it actually has to back up on a day-to-day basis changes significantly. So if you use static policies, you will end up having a lot of spatial skew. So our proposed architecture is basically an adaptive model-based backup management framework, wherein we want to alter or dynamically decide on client-server pairings. This is basically getting away from the static approach of provision time selection. And secondly, we want to alter the timing of the backup. And thirdly, change the backup type based on various indicators in the system, with the objective of minimizing the backup windows on different clients and maximizing the maintenance window, or the unique window available for maintenance on the backup servers. So as a first step, we started by modeling backup server performance. So the utility of this is, in order to do any what-if analysis or optimization, you should be able to do an accurate model of performance, else you can't do a proper optimization. So for this, we selected a random subset of 8 backup servers, and each backup server has 60 days of history of different backups that were performed on these servers. It has a good mix of both full and incremental backups. We tried both multilinear regression and support vector regression, and a couple of alternatives when it comes to modeling granularity. One approach we took was modeling each backup server by itself, agnostic to the client. The second approach is modeling on a per client, per backup server basis. What we found is just modeling on a per backup server basis gives you very limited accuracies. Only about 32% of the jobs we can predict with more than 75% accuracy. But if you do a per client, per backup server model, which is a more fine-grained model, we found that in our initial results, more than 75% of the backups can be predicted with an accuracy of greater than 75%. So we're working on other heuristics to improve the accuracy and then integrate into the optimization framework. Thank you.